Hi, everyone. My name is Lori Peak, and I am the principal investigator for the National Science Foundation supported Converge facility, which is headquartered at the Natural Hazards Center at the University of Colorado Boulder. It is my great pleasure to welcome you to the Converge webinar series. Please note that this webinar is being recorded. The captioned recording and slides will be posted on the Converge website at converge.colorado.edu. Should you have any questions or comments during this brief webinar, please use the Q&A box or the chat box. If we are unable to respond during the webinar, we will provide and post written responses on the Converge webinar webpage for this session. Today, during this webinar, you are going to hear from the leadership of the NSF-funded Structural Extreme Events Reconnaissance, or SIEER, network. The vision of SIEER is to build societal resilience by generating new knowledge of the performance of the built environment through impactful post-disaster reconnaissance disseminated to affected communities. SIEER centers their research and reconnaissance through building capacity and encouraging coordination and collaboration. Over the past 2 years, SIEER has built up a robust membership base and has established regional nodes globally. Today, you will hear from SIEER Associate Director for Data Standards, David Ruch, who is also an Assistant Professor of Structural Engineering at Auburn University. We are also joined by SIEER's director and visionary leader, Tracy Kajewski-Correa, who is a faculty member in civil engineering and global affairs at the University of Notre Dame. I also see that several other members of the SIEER leadership team have logged on today, so welcome. Before I turn this over to our presenters, we wanted to underscore that the SIEER network is actually part of a larger ecosystem of NSF-supported extreme events reconnaissance and research networks. At present, the NSF has funded 7 such networks that are dedicated to geotechnical engineering, the social sciences, nearshore systems, operations and systems engineering, sustainable material management, interdisciplinary science and engineering, and, as you will hear more about today, structural engineering. If you are interested in learning more about these various networks and about how we work together, I hope that you will please visit converge.colorado.edu/research-networks. There, you can find more information on each of these NSF-funded networks and learn how you can get involved. Without further ado, I'm going to stop sharing my slides now so that Tracy can begin sharing the slide deck. And David, I'm going to turn it over to you. Thank you both so much.
All right, and thank you, Lori, and the entire team at Converge for this opportunity to introduce SIEER, the Structural Extreme Events Reconnaissance Network. I am Tracy Kajewski-Correa, the director of SIEER, and before we get started, make sure, are the slides showing okay? Can we get a confirmation of that?
Tracy, they look absolutely great. Thank you.
Confirm. Thank you. And so, yes, as Lori said, I'm the director of SIEER, and I'm pleased to lead this webinar along with David Ruch, our Associate Director for Data Standards. As Lori said, our other associate directors are also online today. Khalid Masalam, who represents our seismic hazards community, David Pravat, who represents our wind hazards community, and Ian Robertson, who represents our coastal hazards community. So we are honored to present on behalf of our colleagues. I will begin today's webinar just by introducing SIEER with a focus on our history and operational elements, our response workflows, and the ways that we engage our members. And then David will take over to focus more on our assessment technologies and the importance of data standards to the work we do as SIEER. Now, natural hazard events provide a critical opportunity to generate knowledge on the performance of the built environment after one of these events impacts an affected community. And field observations initiate what we believe is a vital data to knowledge life cycle. that ideally should feed into continued research and development to address identified vulnerabilities and propose mitigation strategies that most commonly are then disseminated through regulatory mechanisms to ultimately reach affected communities and provide a conclusion to this vital feedback loop. Now, STEER's arrival was intended to better coordinate and leverage these communities of research, policy, and practice to streamline the collection of this data and to, more importantly, accelerate the diffusion of the generated knowledge, not just back to research and development, but actually accelerate it into those affected communities. So following the example of GEAR, our leadership team launched STEER to bring this data to knowledge lifecycle full circle. And our approach is supported by 3 pillars. We believe first in building community capacity, particularly by advancing data standards. We believe also in a commitment to improving coordination so that those teams can then swiftly capture this critical perishable data. And we are committed to inspiring new modalities of collaboration where we can engage diverse stakeholders in our important mission. Now, one thing I want to make a clear point about, what is distinctive, I would say, about STEER is that we were not created like your traditional rapid research, meaning we were not created to explore specific hypotheses that are driven by individual researchers who are interested in collecting proprietary data for their own papers. Rather, we work collectively to generate high-quality communal data that can answer diverse research questions and thus inform continued research by our community. And so we think that is distinctive, as is the fact that we get to stand positioned across the hazards, unifying the wind communities, the earthquake community, and our diverse coastal community by looking at issues that range across the spectrum and synergize those hazards together. Now, as you can see by the map here, we have a global presence already in our early life as an organization. To date, we have more than 300 individuals from around the world who have been approved to be members of STEER. And almost 50% of those people, remarkably, in only the first 2 years, have already participated in our event responses. And we have even enrolled more members in the use of our Fulcrum mobile application that David will talk a little bit more about. That's our data platform. And it shows to us that people beyond STEER's members are finding value in accessing and even contributing to our shared open data platforms. Now, what's important to note about STEER is when we build our teams to respond to an event, most of those individuals have never worked together before. So the question becomes, how can you bring diverse people together quickly to form teams that are effective? And we believe one of the ways we do this is by partitioning their response into 2 vital teams. The first is called our Virtual Assessment Structural Teams, or the VAST. The second is our Field Assessment Structural Teams, or our FAST. Now, those 2 modes of participation are open to our members based on their membership level in STEER, meaning you are assigned to a level in STEER based on your past experience and your degree of training. And over time, you can certainly graduate up to higher levels, but this lets us mobilize our members based on their expertise and experience into the most appropriate roles in our organization. So if you're a level 1 member with very little experience, you start out on our virtual teams. And as you build up experience, you eventually can move on to our field teams at level 2, where you can be a trainee out in the field. And as you get more experience, you can graduate up to level 3, where you are a full-fledged member of our field teams. And eventually even up to level 4, where you are leading the field teams. And those members at our highest levels of 3 and 4 also have the opportunity to join working groups and other committees that help to govern and direct STEER. But this is an effective way we've found to organize our members and be able to mobilize them in event response. And as I said, the virtual aspects of that event response, that virtual reconnaissance piece, is vital to everything we do in STEER. In our responses, we will take on one of 3 tiered levels. At the first tier, we will not form a team of any type, VAST or FAST, because we're instead seeing an event that may not generate potential opportunities for learning, but still deserves some commentary, in which case STEER will release what's called an event briefing, just reiterating some key lessons or learnings. But if the event has the opportunity to generate new knowledge, then we're going to activate at minimum a tier 2 and form one of our virtual assessment teams. And they're going to start collecting information online from public sources to create this preliminary virtual reconnaissance report, what we call the PVRR. And the knowledge generated in that process really helps dictate whether we escalate now to our third level, tier 3, and activate our field teams. Our field teams, these fast teams, are commissioned at the highest level to go out and collect data. And David will talk more about exactly the tools used in that endeavor. And in that process, they'll work with our virtual team to generate the final report, the early access reconnaissance report informed by their observations. And that report is released along with the curated data set, which is, all these products are curated in DesignSafe, and kind of conclude our mission response. At that highest level of mission response, you would then ultimately have up to 3 products being generated along a timeline of a week for the PVRR. A couple weeks later, after the event, you'll have the EARR usually. And then it may take a few months for that curated data to finally arrive in DesignSafe. The reason for this is we have an extensive data enrichment and quality control process using a team of data librarians. Now, what we do is this ensures we have high quality data for our community to reuse, but we also make sure that that data is accessible throughout the process in real time, so our community can still be using it even while we are doing due diligence to make sure that data is highly reliable. Now, when our FAST teams are going out into the field, they need to be equipped with a very specific mission strategy so they can effectively and efficiently collect their data. And our pre-deployment briefings accomplish this and have several modes by which they might engage our members, depending on the hazard type and the opportunity to learn from the event. So I'd like to signal 6 different cases here across 5 different strategies for data collection. Our most common approach is what we call a hazard gradient survey. In this instance, we are conducting a survey by selecting clusters of buildings that we are going to sample along the hazard gradient, so we can see how much the damage varies with intensity. And this kind of data could be used to develop fragilities, describing that damage then as a function of hazard intensity. This is a methodology we've used, for example, in Hurricane Michael, as well as in the Nashville tornadoes earlier this year. In some cases, the conditions on the ground or the amount of time we have in the location might require a different response. We may do a representative performance study, as was the case with the Palu earthquake and tsunami, where here a shorter team duration in the field was intent on documenting a wide class of buildings and infrastructure, not in tremendous detail or with a high level of sampling, but rather to give a broad assessment of representative performance. In the case of the Puerto Rico earthquakes, we had a different approach, conducting targeted case studies where the team developed a very detailed photographic account of specific structures that had particular value. And when it came time for Hurricane Dorian, we went to a completely different approach, a phased multi-hazard investigation, where a small scout team went out to first assess the situation, followed by a larger interdisciplinary team with a range of assessment technologies that was able to document both the performance of structures as well as characterize the hazards in the event. And Hurricane Laura actually challenged us to come up with very new modes of collecting data during a pandemic. So now in this case, we were able to engage small teams in rapid surveys, collecting over 600 miles of street view data that was then posted onto platforms where our virtual teams could safely work from their homes to conduct the damage assessments remotely. So using these different modes, we've had a pretty successful 2 years, I'd say, as STEER. Here's the timeline over which all of that has occurred. We had a pilot in 2017 that actually let us test some of these ideas with hurricanes Harvey, Irma, and Maria. That rolled into STEER version 1.0, which was funded by an EAGER award in 2018, getting our basic protocols and workflows in place. And then with the generous support of the National Science Foundation, we were able to begin deploying. And that has taken us through this last couple years, starting with Hurricane Florence until today. And we're now positioned to present to NSF our STEER version 2.0, which will help us move beyond that initial EAGER award and into long-term operations. In total, we've responded to 33 hazard events around the globe since 2018, about half of those as event briefings, but the remainder using our VAST and FAST teams to generate various levels of detailed reports and data sets. We have 23 citable reports actually in DesignSafe now based on those responses. So with that, I'm going to transition over to David, who's going to talk more about our data collection workflows. And so David, over to you.
All right, thank you, Tracy. Are you able to hear me?
Yes, I am.
Awesome. Well, thank you for that introduction. And so moving on, let's next talk then about some of the nuts and bolts then of the STEER mission lifecycle, from data collection, enhancement, quality control, and then finally to the curation and dissemination. And so about the typical assessment technologies that we use to capture data following a disaster. While traditional deployments may have relied primarily upon a high quality camera and a notebook, some other things to do field notes, STEER has added to this primarily 4 categories of technologies in our assessments that we deploy. The first is mobile applications, such as the Fulcrum app that's kindly provided by Spatial Networks, and soon the Rapid app built by the team at the NSF-funded NARI Rapid Center as well. These can be deployed on a smartphone, and anyone can have access to those as they go into the field. And then second, we have our unmanned aerial systems, which we've used quite often recently, typically focusing on dense imagery captures suitable for reconstruction of high-resolution orthomosaics, 3D point clouds via structure for motion techniques. And then third, we use quite often street-level 360 imaging platforms, which we can use to rapidly capture performance over very large areas. And Tracy alluded earlier to Hurricane Laura as an example of using this. And in fact, I was running the numbers this morning, between Hurricanes Laura and Delta, our teams collected over 1,000 miles of 60 megapixel panoramas, 360 panoramas at 4-meter spacing throughout affected areas in Louisiana and Texas that were hugely critical in allowing us to collect this data set ethically, even in the midst of the COVID pandemic. And so this has been a very useful platform for us. And then lastly, we also use terrestrial scanning technologies, including mobile and stationary LiDAR, often using these to perform more detailed case studies and getting dense point clouds of key structures or clusters of interest. I do want to point out, though, that while we use all of these technologies, we also, you don't have to have these technologies in your lab in order to participate. In other words, these technologies or lack of them should not be a barrier to your participation. While we encourage STEER members to bring their own equipment if they have it and are comfortable using it, the NSF-funded NARI Rapid Center, again, has proven to be a fantastic resource for getting us any of these technologies in a timely fashion, with training materials on how to use it properly and full-time support while in the field. And so even if you don't have access to these in your own lab, we still encourage participation. So next slide. So next, let's talk briefly about our mobile apps, because these in a way set the structure of the data sets that we ultimately generate for buildings and other structures. The purpose in using these apps is to combine multiple data types, including the survey data itself, which may be multiple choice or single choice select forms that we can custom generate, as well as photos, video, audio, other data, all into a single geolocated record that can be synced to a cloud platform in real time. The advantage of this is that this allows the VAS and the STEER leadership to see in near real time where the teams are at, get preliminary looks at the data being collected, even begin using the data to populate the early access reconnaissance reports and other products, and share with some of our partners and that are also interested in these areas. And so using a mobile app also gives structure to the investigator on site as well. We talked about how we have a level 2 FAST member who may be training, and being able to have a mobile app gives some structure, prompting them for key things to look for that they may not know to capture otherwise. And then finally, what I see as a key advantage of using mobile apps like the Fulcrum platform we're using now, or the RAP here shortly, is that we're not just collecting data, we're building a database in real time. We no longer have to come out of the field and sort through thousands of photos and associate photos of the same building together, geotag, assign basic attributes. All that's being done live in the field. It's being shared in real time, and we're coming out with a database that we can immediately begin to analyze and learn from. So next slide. So next, let's talk about our mission design. And so our preferred strategy is to pre-select deployment locations, either at the individual building or the block scale, informed by pre and post satellite imagery, social media reports, local connections, and oftentimes intelligence provided by partners such as FEMA. And the idea is that we want to take some pressure off of our FAST by identifying and prioritizing important target areas for them before they get into the field. And this ensures that we make efficient use of our time while in the field, which is, if you've been in the field, you know how precious that time is. And it also improves the likelihood that the data that we collect ultimately goes back and meets our mission objectives, as Tracy talked about earlier, whether that be representative samples or detailed inspections, et cetera. It helps set the strategy for collecting the necessary data for those. And so this same strategy also works well with our rapid imaging team, such as Street View. You think about it in a hurricane or an earthquake. I mean, there's thousands of miles of roadways affected and buildings affected, and you can't capture them all. So it's important for us to be able to objectively identify key routes, key clusters to focus on. And that is a key element of our mission. But with all that said, ultimately, these pre-selected targets are just recommendations, perhaps strong recommendations, but we ensure that our FAST also have freedom to adjust as needed in the field based on access, new information, et cetera, et cetera. The flexibility there is key. So next slide. Oh, I think, did you skip one? There you go. So once we've identified a cluster of interest, we prefer a mixed methodological data collection strategy. And by that, I mean each data collection technology that I referred to earlier, the UAV, Street View, LiDAR, door-to-door assessments, they each have their own strengths and weaknesses. And ultimately, we get the most information out of combining them. And this is particularly effective in important clusters of structures in an event where we may deploy UAV, for example, as shown here, to capture some high resolution aerials, maybe 3D models for mapping, the roof slopes, maybe automated classification of roof damage. But then simultaneously, we also deploy Street View cameras to ensure we have good ground level imagery to be able to identify things like fenestration protection in a hurricane or soft stories in an earthquake or damage to the vertical elements of the building. And then finally, there is still great value in detailed on-site investigations by structural engineers to be able to understand the load path, the construction quality, details of the observed damage that are just not going to get captured by these remote sensing methodologies. So obviously we can't use this approach everywhere in terms of these overlapping technologies, but in important clusters, this has been an effective strategy and is our preferred choice depending on the type of mission it is. And for example, again, going back to Hurricane Laura as one example, there we were able to document the performance of several brand new neighborhoods impacted by a design level event at a large scale with the Street View cameras. But then Justin Marshall and myself were also able to go in and perform a couple of detailed forensic load path assessments in those same neighborhoods that documented some of the key structural details and connections that we could then extrapolate to the rest of the cluster. And so these types of approaches are critical to ensuring that we have both sufficient depth and breadth to our assessments, which is always a challenge in events like this. The next slide. So then once we've collected the data, a critical component of our workflow at STEER is what we call the data enrichment and quality control process, or DEIQC. So the key idea here is that our FAST obviously only have limited time in the field. And further, they also don't always have access to all the information they need to properly define or contextualize the performance they are documented. They're also trying to move literally fast and may make a mistake in the field or just have to use engineering judgment to assume something. And so to complement our FAST, we tap into our network of VAST and the student data librarians to enhance the FAST field data, and then pass this enhanced data set through a rigorous quality control protocol to ultimately ensure the data being published is robust, of high quality, and reliable for reuse and analysis and knowledge mining later on. And long term, we're exploring, there's a lot of potential here for some automated tools to facilitate this process, harnessing AI, establishing human-machine interfaces for accelerating this process and ultimately accelerating the creation and publication of these final data sets. But ultimately, we recognize that you go into the field and there's a variety of data that's important to defining and contextualizing the performance of a given structure. For example, assigning a damage rating or identifying the year of construction or other attributes of the building, or maybe the structural system itself and some of the materials used. So some of this data we recognize is absolutely critical for the on-site FAST member to collect, but a lot of it can be sourced remotely once you have photos and can tie into the other supplemental data sources. And therefore, it's much more efficient then to allow our vast members or data librarians to collect this information. And then this also provides a fantastic training opportunity for them to be able to see what information is important to collect, get familiar with the variety of structural systems used, for example, and ultimately be better prepared to contribute to FAST missions and future events. And so here's just an example of some of the supplemental data sources that the DEIQC process may rely on. For example, we have the raw data in Fulcrum. We have public data housed in, a county assessor office or other offices like that. You have the dense points clouds from the Structure for Motion. You have high resolution aerial imagery, either from, again, the UAVs or from other sources, maybe obliques from pictometry or the Geospatial Imaging Consortium, and then our 360 panoramas. Collectively, these sources can all be mined to supplement the on-site field data and improve the quality and depth of the assessments and the data sets that are being generated from these reconnaissance missions. And then lastly, the final step in our data collection workflow, if you will, is the dissemination. And this is not just an afterthought for us, as Tracy alluded to earlier. Thinking back at many of our leadership meetings, I can't tell you how many hours we spent discussing how best to disseminate both the data and the findings to the wide range of stakeholders that are interested in it. As she mentioned, our ultimate goal at STEER is not just to collect data, it's to build resilience through reconnaissance. And so if our data, our findings, recommendations, if that all stays within the structural engineering community or even within our academic silos, it's not going to do a whole lot of good to the communities who really need this information. And so while we're still developing some new approaches, right now we have 4 primary modes of data and knowledge dissemination. So the first is rapid publication of our street level 360 panoramas to either Google Street View or more recently to Mapillary. And these give FEMA, public officials, communities, other researchers access to really vast quantities of data via these widely used and public platforms, typically within a couple days of the data being captured. Also, through our use of the Fulcrum platform up in the top right, we're able to share the individual field assessments in real time through the Fulcrum community, which allows anyone to be able to see what on-site data we're collecting, as well as the various damage classifications and other attributes being assigned. And this link remains active even throughout the DEIQC process. So as we update and refine and enhance this data, it remains publicly available to those that are interested in it. And then we also disseminate to our library of reports from the PVRR and EARR and event briefings that Tracy mentioned earlier, and the hybrids of these that we've done recently. They get emailed out to our distribution list that anyone can sign up for, and then pushed on social media platforms as well. And then finally, DesignSafe is the repository for all of our data and reports for a given response, allowing anyone to go and use our data to pursue their own hypothesis-driven research ideas. And we've had a number of data sets published already, with several more big ones that are coming very soon. And we strongly encourage you to use these data sets as you see fit, and reach out to us if you have any questions about the content, methodology, anything else, and leverage this data for your own projects. And so with that brief overview, I'll go ahead and turn it back over to Tracy.
Great, thanks, David. So just to keep us on time, I just want to wrap up, and I will just go straight to acknowledgements because I know Lori has some concluding remarks, but we just want to take a moment to express our appreciation to NSF, to Converge, and all the other EERs who work with us to share knowledge, the generosity of folks like Spatial Networks, but our wider partners in NERI, and just our STEER members. They make this possible, and they make tremendous sacrifices to go out and get that data. And we welcome you to join our efforts at STEER, and you can apply there. We have a Slack channel, and those are great ways to stay connected with us and know when we're responding and deploying to events so you can sign up and help. So Lori, I will kick it back over to you.
Okay, thank you so much, David and Tracy, for the presentation. And thank you to everyone out there who joined us today. And I especially wanted to say to David and to Peter, we see your questions in the chat box, and please know that we will get written responses that we will email directly to you, and we'll also post on the Converge website in the interest of time today. So if anyone else has any questions, please go ahead and drop those in the chat box. But for now, we are going to go ahead and pull this car over to the side of the road. But again, we just really wanted to thank the entire STEER leadership team for all of the progress that you have made in this space and the connections that you have made to other engineering groups in the field, as well as to the social sciences and across various other disciplinary communities. So thank you to our presenters. We also wanted to offer a special thanks to the National Science Foundation, to our program directors, Joy Pauschke and Jack Mazzaros, for all of their support of the various efforts that you heard about today and many that you'll be hearing about in the future. Please remember, everyone, that we will post this webinar recording and the slides from Tracy and David and the STEER leadership team at converge.colorado.edu. And we hope you will sign up for more free resources and upcoming events through our Converge website. And if you have any questions, please contact us at converge@colorado.edu. Everyone, please have a good rest of the day, and please remember to take care of yourself and others. Thank you, Tracy and David.
Thank you, Lori.
Thank you.